Welcome to the Advanced RAG series. Here's a number that should stop you in your tracks. Over 70% of RAG systems in production today struggle not because they fail to retrieve the right documents, but because they serve them in the wrong order. Let that sink in. The search works, the ranking does not. That is exactly what this course is about. Over 6 modules, we are going to crack open the re-ranking layer, the secret weapon that separates a decent RAG pipeline from a phenomenal one. Think of it this way. Retrieval is like fishing with a net. You pull up a big haul, but re-ranking, that is the expert chef who picks out the 3 perfect fish for tonight's dinner. By the end of this series, you will know how to build that chef into your pipeline. Ready? Let's dive into Module 1. Quick question. If you search for best Italian restaurant near me, would you trust a result just because the search engine found it first? Probably not. You would want the most relevant one at the top, right? That is exactly the problem with vector retrieval. It returns results ranked by embedding distance, how mathematically close 2 vectors are. But mathematical closeness and actual relevance are not the same thing. Look at this example. Doc C is clearly the most relevant to our query, but vector search buried it at rank 3. After re-ranking, it jumps to the top where it belongs. Imagine sending a student to a library and they come back with 5 books. The best one is tucked in the middle of the stack. Re-ranking is the act of flipping through and putting the best book on top. So how do we actually build this re-ranking step into a pipeline? That is what the next slide reveals. Here is the big shift that changed everything in RAG design. Before re-ranking, pipelines were simple. Retrieve your top K documents and throw them straight at the LLM. Sounds efficient, right? But here's the problem. You are feeding your LLM a buffet of information where the tastiest dish might be buried under 3 plates of stale bread. The after pipeline adds one crucial step. Between retrieval and the LLM, we insert a reranker, a precision filter that rescores every candidate against the original query. Think of vector retrieval as casting a wide fishing net. You catch a lot, and that's great. But the reranker is your quality inspector on the dock, sorting the catch and handing only the freshest fish to the chef. The biggest quality gain happens right at the top, positions 1, 2, 3. That's where your LLM looks first. Now what happens when you skip this step? The costs are real, and they might surprise you. Let me hit you with a stat that keeps RAG engineers up at night. When your top 3 documents are misranked, not missing, just in the wrong order, hallucination rates spike by 40%. 40%! And it gets worse. Teams see 3 to 5 times more LLM retries because the model keeps getting incomplete or stale context. About 30% of your precious context window wasted on irrelevant documents that should never have been there. Here's what makes this so frustrating. These are not retrieval failures. The right document was found. It was sitting right there in your results. It just wasn't surfaced to the top. Imagine you're a doctor, and the patient's correct diagnosis is in the file, but it's buried on page 7. You might miss it entirely. That is what bad ranking does to your LLM. So how do we fix this? There are 3 major approaches, and each one has a completely different philosophy. 3 tools, 1 mission. Figure out which document actually answers the question. First up, LLM-based reranking. You literally ask your language model to judge each document's relevance. It is the most flexible and the most accurate, but also the slowest and most expensive, like hiring a master sommelier to taste every wine in the cellar. Next, cross-encoders. These are purpose-built neural models that evaluate the query and document together as a single input. They are the production sweet spot, fast enough for real-time, accurate enough for serious work. Think of them as a highly trained wine buyer who can assess a bottle in seconds. Finally, rule-based re-ranking. No AI needed. Pure business logic. Boost documents that are fresh, from trusted sources, or match a specific type. It is like having a store policy that says always display the newest vintage first. Each one shines in different scenarios. Let us start with the most powerful one, using an LLM as your relevance judge. What if I told you that the LLM you are already using can double as a ranking engine? No new model to deploy, no extra infrastructure. You just ask it a question. Here's how it works. You take your query, pair it with each candidate document, and ask the LLM a simple prompt. Given this query, Rate this document's relevance from 1 to 10. The LLM reads both pieces deeply, understands nuance, context, even implied meaning, and gives you a score. Imagine you are a teacher grading essays. You do not just check if the student mentioned the right keywords. You read the whole response and judge whether it truly answers the question. That is what the LLM is doing here. The beauty is that you get deep semantic understanding. The trade-off is speed and cost. You are running a full LLM inference for every single candidate. So when is it worth it? When accuracy is everything and you have the latency budget. Let's see exactly what this scoring looks like in practice. Let us walk through a real example so this clicks. Someone searches, what are the side effects of ibuprofen? 2 documents come back. Doc A talks specifically about stomach upset, headache, and dizziness from ibuprofen. Doc B gives a general overview of NSAIDs as a drug class. Now, a vector search might rank these similarly. Both are semantically close to the query. But watch what happens when the LLM scores them. Doc A gets a 9 out of 10 because it directly addresses the specific question about side effects. Doc B gets a 4. It's related, sure, but it's like asking about the weather in Paris and getting a geography textbook about France. Relevant, technically. Helpful? Not really. This is the magic of LLM re-ranking. It understands intent, not just similarity. Each document is scored independently, and the re-ranker spits out a new ordered list. It's not generating an answer. It's just putting the best evidence first. But this power comes at a price. How does it stack up against the alternatives? Time for a head-to-head comparison. And I want you to think of this like choosing a car. The LLM Reranker is your luxury sedan, 5-star accuracy, incredibly comfortable ride, but expensive to fuel and not the fastest off the line. Latency runs 100 to 500 milliseconds per candidate, and every candidate costs you tokens. The Cross-Encoder is your sports sedan, 4-star accuracy, 20 to 80 milliseconds, and 0 token cost because it's a dedicated model. The rule-based approach is your reliable commuter. Basic accuracy but nearly instantaneous, completely free, and you can pop the hood and see exactly how it works. Notice the trade-offs. The LLM gives you explainability through its prompts, but the Cross-Encoder is a black box. Rule-based is fully auditable. No single approach wins everywhere, and that is actually the key insight. Use LLM re-ranking when accuracy is your North Star, and you can afford the latency. Now let's dive deep into that sports sedan. This is one of my favorite concepts to explain because the difference is so elegant. A bi-encoder, what your vector retrieval uses, processes the query and document completely separately. It turns each one into a vector, then compares them with cosine similarity. Fast? Absolutely. You can pre-compute all your document vectors offline. But here's the catch. The query and document never actually see each other during encoding. It's like 2 people writing letters about the same topic without ever talking. They might agree, but they miss the nuances. A cross-encoder changes everything. It takes the query and document, concatenates them into a single input, and feeds them through the transformer together. Every token in the query can attend to every token in the document. It's like putting those 2 people in the same room for a conversation. The understanding goes way deeper. The trade-off? You cannot pre-compute anything because the score depends on the specific query-document pair. Let me show you the mechanics. You take the query and document, stitch them together with special separator tokens, CLS at the start, SEP between them, SEP at the end. This combined sequence goes through the transformer encoder, and out comes a single relevance score between 0 and 1. In our example, that score is 0.87, highly relevant. The critical thing to understand is that this runs once per candidate document. There's no pre-computation trick. Every query document pair gets its own forward pass through the model. Think of it like a taste test. A bi-encoder gives each dish a score on its own. A cross-encoder tastes the dish while thinking about what you specifically asked for. Does this pasta work for someone who wanted something light? That context changes the score. The popular models in this space are MS Marco Mini LM for speed, BGE Reranker Large for accuracy, and Cohere Rerank if you want a managed API with multilingual support. But enough theory. Let us see the dramatic before and after of what a cross-encoder does to real search results. This is where it gets really satisfying. Someone queries best practices for handling null pointers in C++. Look at the vector retrieval order. Rank 1 is a broad C++ memory management overview, related but not targeted. Rank 2 is about null pointer exceptions in Java, wrong language entirely. The most relevant document about nulptar versus null in modern C++ is buried at rank 5. Now watch the cross-encoder work its magic. After re-ranking, nulptar versus null jumps to rank 1. Smart pointers and RAII, directly relevant to safe pointer handling, moves to rank 2. The Java article drops to the bottom where it belongs. The top 2 positions now carry exactly the context your LLM needs. No noise, no wrong language distractions. This is the difference between your LLM getting a clear, focused answer and it getting confused by a Java article when the user asked about C++. But here's a question. What about signals that no neural model can pick up? Things like document freshness, source authority, file type? That is where our third approach enters the picture. Pop quiz. If 2 documents have nearly identical semantic similarity scores, but one was written in 2019 and the other in 2024, which should rank higher? The 2024 one, obviously. But here's the thing. Your embedding model has absolutely no idea when either document was written. Vectors encode meaning, not metadata. And this gap is bigger than most people realize. A 2019 document can outrank a 2024 update. A random blog post can outrank your internal company policy. A forum discussion can outrank the official technical specification. The embedding model is doing its job perfectly. It is measuring semantic similarity. But semantic similarity is not the whole picture. It is like judging a book solely by how relevant its title sounds, without checking who wrote it, when it was published, or whether it is even the right genre. This is the gap that rule-based re-ranking fills, applying business logic that vectors literally cannot encode. And there are 5 specific signals that make the biggest difference. 5 signals that can completely change your ranking. And none of them live inside an embedding vector. First, freshness. Newer documents get a boost, older ones get penalized. In fast-moving fields like tech or compliance, last year's answer might be dangerously wrong today. Second, source authority. An internal policy document should always outrank an external blog post when someone asks about company procedure. Trust matters. Third, exact match. If someone types a specific product ID or error code and a document contains that exact string, give it a hard boost. Vectors might soften that match, but business logic should not. Fourth, document type. When someone asks a direct question, an FAQ should rank above a lengthy white paper. Match the format to the intent. Fifth, policy priority. Compliance documents always surface above general content. No exceptions, no machine learning needed. Think of these like a librarian's rules, automated common sense applied after the search engine does its mathematical work. But how do you actually combine these signals into a single score? Let us do the math together with a real scenario. Someone searches expense reimbursement policy for remote employees. 4 documents come back. The travel expense guide from 2019 has the highest vector score, 0.91, but it is 5 years old, external, and not the right document type. After applying our rules, it drops to rank 3. The remote work policy from 2024 has a lower vector score, 0.88, but it gets massive boosts. Plus 15 for freshness, plus 10 for being an internal source, plus 10 for matching the document type. Its rule total of 35 catapults it to rank 1. See the formula at the bottom? It is beautifully simple. Take the vector score, multiply by 100, then add your metadata boosts. No neural network, no GPU, just arithmetic that encodes your organization's priorities. Imagine explaining to a compliance officer how your system ranked results. With rule-based scoring, you can point to every single number. Try doing that with a neural network. Now that you know all 3 approaches, the big question becomes, which one do you actually use? This is the slide I want you to photograph, because it is going to save you hours of architectural debates. Think of choosing a re-ranker like choosing the right tool from a toolbox. You would not use a sledgehammer to hang a picture frame. If your hard constraint is latency under 100 milliseconds, The LLM Reranker is out immediately. It is simply too slow. Cross-encoders and rule-based are your options. If accuracy is absolutely critical, legal research, medical Q&A, compliance, the LLM Reranker is your best bet, with cross-encoders as a strong runner-up. Rule-based cannot match their semantic depth. If you have no model infrastructure at all, the LLM Reranker works via API, and rule-based needs only code logic. Cross-encoders need a model deployed somewhere. Here is the key insight at the bottom. No single method wins every dimension. That is not a weakness of the framework. That is the reality of engineering trade-offs. And that is exactly why most production systems use hybrids. But which combination works for which real-world scenario? Let me give you 3 scenarios you will absolutely encounter in the real world. Scenario 1. You are building a real-time chatbot or voice assistant. Users expect answers in under a second. Use a cross-encoder. Models like Mini-LM score in 20 to 50 milliseconds. Good enough accuracy at acceptable speed. Do not even think about an LLM Reranker here. 200 to 500 milliseconds of extra latency and your users will leave. Scenario 2. Legal research, medical Q&A, compliance systems. Wrong answers have real consequences. Use an LLM Reranker. The extra latency is worth it because the LLM understands jurisdiction, clinical terminology, and nuance that fixed models miss. Scenario 3. You are dealing with policy documents, versioned content, regulated data. Use rule-based reranking. It is auditable, deterministic, and your compliance team can literally read the scoring logic. No black box to explain. But here's what makes great engineers great. These are starting points, not finish lines. Most production systems combine 2 or even all 3. Can you really stack all of them? Yes, you can. And honestly, this is the architecture I recommend for any high-stakes RAG application. Picture a funnel. At the top, vector retrieval casts the wide net. You pull back your top 100 candidates. Stage 2, the rule filter kicks in. Apply freshness boosts, source authority, knock out stale or untrusted documents. You are down to 50. Stage 3, the cross-encoder rescores those 50 candidates with deep semantic understanding. You select the top 10. Stage 4, and this is the precision layer. The LLM Reranker does a final pass on just those 10 candidates. Only the top 3 survive to reach the LLM for answer generation. See what happened? Each stage narrowed the funnel further. Rules handled what vectors miss. The cross-encoder added semantic depth. The LLM applied final judgment on a tiny set, so cost and latency stay manageable. It is like a talent competition. Auditions, then callbacks, then finals, then the winner. Now let's zoom out and see how this fits into the complete end-to-end pipeline. Here's the full picture, and I want you to see how beautifully everything connects. 5 stages. Stage 1, the user asks a question. Simple. Stage 2, we embed the query and retrieve the top 100 candidates. Wide net, fast execution. Stage 3, the Reranker scores and reorders those candidates. This is the first critical decision point. Everything we have learned about LLM Rerankers, cross-encoders, and rule-based scoring happens right here. Stage 4, filter and select. This is the second decision point, where we apply the context budget cut. How many documents actually make it to the LLM? Stage 5, the LLM generates an answer from that curated, ranked, filtered context. Notice something important. The final context window is curated, not raw. The LLM never sees the messy, unranked pile of 100 documents. It sees the top 5, carefully chosen and ordered. This pipeline is elegant, but the order of operations inside it matters more than you might think. Should you filter before or after re-ranking? This question has tripped up a lot of smart engineers. This is a design decision that sounds trivial, but can completely make or break your pipeline. Option A, filter first, then re-rank. You apply your metadata filters and remove documents before the re-ranker ever sees them. Sounds logical, right? Here is the danger. What if your freshness filter removes a 2022 document that happens to be the single most relevant result? The re-ranker never gets a chance to boost it. Gone forever. Option B, re-rank first, then filter. The re-ranker sees every candidate and scores them all on semantic relevance. Then you apply your business rules on the ranked list. The critical difference? The re-ranker had access to the full picture. No candidate was prematurely eliminated. Think of it like judging a cooking competition. Option A is eliminating contestants based on their resume before they cook. Option B is letting everyone cook, tasting all the dishes, and then checking qualifications. You get much better results when the judge sees all the options first. So we know the order: re-rank, then filter. But how many documents should actually survive to reach the LLM? Here is a counterintuitive truth. More context often makes your answers worse, not better. The sweet spot for most RAG queries is just 3 to 5 tightly relevant chunks. When teams send the full top 10 without filtering, accuracy drops by about 20%. And by using re-rank then select instead of sending the full top K, you save roughly 50% of your tokens. Think about it like studying for an exam. If someone gives you the 3 most relevant textbook pages, you will ace it. If they dump 30 pages on your desk, most of them tangentially related, you will get confused, miss the key points, and probably panic. Your LLM feels the same way. Here is the smart selection rule. After re-ranking, do not just grab a fixed number like always take top 5. Instead, set a relevance score threshold and take every document above it. Sometimes that is 3 documents, sometimes it is 7. Let the quality of the results decide, not an arbitrary number. We are almost at the finish line. But before we wrap up, there are 3 failure modes that catch even experienced engineers off guard. 3 traps that are invisible in your retrieval metrics but will absolutely show up in your answer quality. Trap 1. Over-retrieval. Fetching the top 50 candidates when the top 10 would suffice. It sounds harmless, but you are bloating your re-ranker's workload and introducing noise. Every extra candidate is a chance for a mediocre document to sneak through. Start with 20 to 30 and tune from there. Trap 2. Stale metadata. Your rule-based scoring boosts documents based on freshness and source authority. But what if those metadata fields have not been refreshed in months? You are boosting based on lies. Set up automatic re-indexing whenever documents are updated. Trap 3. The latency trap. You fell in love with your LLM re-ranker's accuracy, so you put it on every single query, including your real-time search path. Suddenly, your P99 latency is through the roof. Reserve LLM re-ranking for async or low-traffic paths. Use cross-encoders for interactive queries. These are the kinds of lessons that usually cost teams weeks of debugging. Now let us bring everything together. Here it all is, on one slide. Your cheat sheet for everything we covered. 3 re-ranking methods, each with a clear strength and a clear watch-out. LLM re-rankers give you the highest accuracy, but cost you latency and tokens. Cross-encoders hit the sweet spot of speed and precision, but need model infrastructure. Rule-based is free, auditable, and perfect for policy, but it cannot understand meaning. And the hybrid approach? It gives you the best of all 3, with the trade-off being pipeline complexity. 5 rules to live by. Retrieve wide but re-rank narrow. Always re-rank before filtering. Use score thresholds, not fixed numbers. Cross-encoders for real-time and LLMs for async. And layer in rules wherever business logic exists. You now have a complete mental model for building production-grade re-ranking into any RAG pipeline. The question is not whether you need re-ranking. It is which combination fits your specific constraints. Go build something amazing with this.